Hi, everybody. These are the notes for section 3.2. In this module, we are doing section 3.2, which is addition and subtraction of whole numbers, as well as 3.3, which is multiplication and division. They will be separate videos and separate PDFs of notes, just so you're aware. So there's going to be 2 videos for you guys to manage in this section. All right, so when we talk about addition and subtraction of whole numbers, we're talking about these kinds of standards. We're talking about primary grades for the most part. So kids in 3rd grade are asked to fluently add and subtract within 1,000 using all different kinds of strategies and algorithms. They have to understand the value of place value and get how numbers are built. They have to understand the properties of operations and the relationship between addition and subtraction. They also have to fluently multiply and divide. We'll talk about that next. And then they have to solve problems that are more than one step using those 4 operations, writing equations, and finding reasonableness of answers, saying like, hey, does this make sense, using mental math and estimation. When we're talking about addition and subtraction of whole numbers, we need to remember where whole numbers live. So whole numbers are here, okay? Whole numbers are basically all of the natural numbers. So the numbers you count on your fingers, 1, 2, 3, 4, 5, 6, 7 onwards, as well as 0. Okay, there's no fractions, there's no decimals yet, there's no negative numbers yet. When we're talking about whole numbers, we're really just talking about things you count on your fingers as well as 0. So there are a number of models of addition that are really important for kids to get. So it's important that you do all of them. And one model will make more sense to a kid than another, but that doesn't mean you shouldn't show them all of them because it helps them be flexible with numbers. So when we talk about counting on, it's when a kid begins to count from one number and counts, begins with a number and counts forward from it. So like my daughter is in 1st grade, we've done some of this with her. If I was asking her to add 4 and 6, what I would want her to hear, what I would want to hear her say, or what she thinks out loud is, I want to hear her say 4. And then whether she used counters or her fingers or whatever she needs to do, I would want 4, and then she'd go 5, 6, 7, 8, 9, 10. And this is 6, okay? So 4 and 6 is 10. You don't want them to start at 0. You don't want them to go 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10. You want them to start from the number that's beginning and count on. That's the idea here. The second model is back to sets like we've been seeing. So in addition, technically we can think about this as a union of disjoint sets. So 2 sets, right? Disjoint means they have no overlap, set A and set B. And if we have the or, we take everything from both of them. The number of things in A or B is the number of things in A and the number of things in B, or, okay? So in this case, set B has 4 things, set A has 6 things. There's no overlap. So when I have the or, I take everything from both sets, I end up with 10 things. So we can think of addition like overlap, or not overlap, combining 2 disjoint sets. Remember that n of something is the cardinal number, is the number of things in that set. You don't always set it up like this for kids. You're not talking about disjoint with them. We're not talking about unions, right? But you will have them, have a group of counters of 6, a group of counters of 4, and they'd combine them together into 10 counters. That's 2 disjoint sets, okay? This is the formal addition, so formal definition. If A and B are disjoint sets, then n of A equals little a, n of B equals little b, and A plus B is the n of A or B. A and B, just as a vocabulary thing, small a, small b, the ones up here, are addends, okay? And A plus B is the sum, which you probably knew. The other model that's super important is a number line. Number lines carry with a kid in math from kindergarten all the way up through middle school, because you can use all kinds of, you can do all kinds of math on a number line. It's really important that kids get comfortable with a number line in primary grades and K1, 2, 3, so that they can then use it to their advantage in later grades when they're doing more complicated math, when they're using more complex ideas. So when we model addition, we use arrows, vectors, on a number line. The sum of two numbers is found by putting the initial point of the first arrow at 0, putting the next point, the initial point of the second arrow at the end of the first arrow. That's what that means, terminal point. And then the sum is indicated by where the second arrow ends. So that sounds insane. It's not as complicated as it sounds. So if I have 6 plus 4, okay, and somehow this is shifted. I need to move my picture over. Why won't it go? This should be at 0. Sorry. Every now and then my pictures don't stick to where they belong. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Boy, this drawing is bad all the way around. We might just make a new one. So if we have our number lines here, we're adding 6 plus 4. What we would want to see is the point, the first point here. Oh, where's my pen? Sorry, I'm having some technical issues today. So here's my first point here. I would want that arrow to draw to 6. Okay? This is the terminal point of the first vector. So here's the beginning, here's the terminal point. From there, I want the kid to draw on, because we're counting on, 4 more, right? So we go from here to here. The terminal point of my second vector is at 10. So this is 6 plus 4. You want them to label their vectors. And then you want them to draw one that shows the whole sum. So 6 plus 4 is 10. It's always going to look kind of strange to have that many arrows, but that's what's happening here. Okay, you always want them to start from 0. Some of my pictures are off, I see. All right, and if we look at this, this is exactly what we're talking about. They want to represent the number 5 here. The problem is that this yellow line doesn't start at 0. This should be a vector straight, starting at 0 with a point, and terminating, the terminal end of the vector should be at 5. Okay, so, you know, and kids do this with rulers too. I bet if you gave, 10 of your friends a ruler, you'd find a fair percentage that would start at 1 instead of 0. It's a pretty common thing to do wrong on a number line and with a ruler. So you do need to be a little bit careful. All right, there are some games in this section and in the next one. They are going to be games that you play with a partner as a part of your written assignment. So here's the instructions for addition Toppet in a less PC world. This is war, but it is a really common game for younger kids to play. You can play with 3 players or 4 players or 2 players, but do read the directions and think about the answers down here. There are going to be some questions for you to answer after you play this game. Okay, the idea is the largest sum wins the cards. Okay, all right. When we start to talk about addition and subtraction and other things, the other thing that we have to do is order numbers, okay? We have to start to have kids understand that they can order numbers on a number line and compare them, right? So when we order whole numbers, there's a formal definition. And again, you're not doing formal definitions with first graders, but it's useful for you as a grown-up to have the formal definitions, in your pocket for when you need them. So the formal definition of ordering numbers is for any whole numbers A and B. A is less than B, written as A less than B, if and only if there exists a natural number K, something, that you can add to A and make it equal B. So A is less than B if A and something can get you to B. If A is less than B, it's to the left of B on the number line. This is a really important thing for primary kids to get, because eventually when they get to negative numbers, all of a sudden it makes their head spin a little bit. But if they know the smaller number is always to the left, when they compare -5 to 1, they're not going to be as freaked out, because what happens is when kids get to negative numbers, they go like, wait, -5's got to be bigger. A 5 is bigger than a 1. But it's to the left on the number line, and we know that the thing on the left is always smaller. So we are into properties now. There is an important property called the closure property of addition of whole numbers. If A and B are whole numbers, then A plus B is also a whole number. What we use this for is to determine if a set is closed or not. What it means when a set is closed, and this is important, this is kind of a tricky thing in this section, and it will reappear. A set is closed when you can add, or sorry, under addition. It's different for different operations. So for addition, how closure works is if you take all of the things inside a set, if you add any two items, elements in that set together, and the answer, the sum, is still inside the set, anytime you do it, then the set is closed. Excuse me. If you add those two numbers, elements together, and it's not inside the set is not closed. Now, in closure, sets are either closed or not closed. It's not closed and open. It's not like a door, okay? So let's look at this one. This one says set E equals 2 times n, where n is any element of the whole numbers. Okay, so what does that actually mean? Well, it means, think about numbers that would work. So if, why won't that work? If n is 1, 2 times 1 is 2. If n is 2, 2 times 2 is 4. If n is 3, 3 times 2 is 6. Are we going to come to any number that isn't a whole number here? You might have to stop and think about it for a second. Okay. No, we're not, are we? So it's got to be closed. All right. So let's see. So anything that I can put into here is going to give me double, and that's going to work out. This is the definition of even. All right. Even numbers added together, oh boy, are always even. So these are the numbers in my set. So if I add 2 and 4, I could get 6. If I add 2 and 6, I'm going to get 8. If I add 4 and 6, I'm going to get 10. Am I ever going to get an odd number? No, right? Any even plus even, it's always going to be even. So no matter what I add together here, I'm going to get an even number, and this set is all even numbers. So it's closed, because no matter what I add together, I get something else that's actually still in my set. So then let's look at the next one. Set F is 2n plus 1, where n is an element of the whole numbers again. So let's find out what's in it first. So let's see, if n is 1, 2n plus 1 is 3. If n is 2, 2n plus 1 is 5. If n is 3, 2n plus 1 is 7. All right, so these are the numbers in my set. These are, what kind of numbers do you get here? These are odd, right? So odd numbers. So this set contains all of the odd numbers. Now let's think for a second. If I add an odd number plus an odd number, what do I get? Well, look. If I add 3 plus 5, what do I get? I get an even number. If I get 5 plus 7, what do I get? I get an even number. Odd plus odd is even. Well, that's a problem, because my set only has odd numbers in it. So if my set is made of odd numbers, but every time I add two numbers together, I get an even number, and it's not in my set, that's not closed. All right, and the last one is tricky. So I have this set G, it's only got 0 in it and 3 in it. So is it closed or not closed? Well, I want to see, any two numbers I add together, right? If I had 0 plus 3, that's 3. If I had 3 plus 0, that's in the set. So what do you think? It's actually not closed. And I wonder if you figured out why. Think for a second about why it's not closed. Sorry, my pen and I are having a disagreement here. So in this case, one of the other things that can happen is there's no rule against adding something together more than once. So what I could do here is I could add 3 plus 3. And that's 6, which is definitely not in my set, which means this is not closed, okay? Because I can add two numbers together and get something not included in my set. Another property of addition is that addition is commutative. What that means is turnaround facts, right? A plus B is the same as B plus A. 3 plus 4 is the same as 4 plus 3. It's actually a really hard thing for little kids to understand. They think every problem is different, right? 3 plus 4 and 4 plus 3, they haven't made the connection yet that those are the same fact in a different order. So it's something, turnaround facts are something they talk a lot about in primary grades because of that, because it's not just a natural thing for kids to grab. We can use both the set model and the number line model to show the commutative property. So if I have a set, this set can have 1, 2, 3 things in it. This set can have 4 things in it. And they don't have to be the same things. I don't want them to overlap. When I have the or, I have these 3 things, or these 4 things. I make 7 things, right? 3 plus 4 is 7. 4 plus 3 is 7. On a number line, let me change colors. So if I have 0, 1, 2, 3, 4, excuse my ugly number line, 6, 7, right? I could do start at 0, go to 3, add on 4, gets me to 7, right? But I could also start at 0, go to 4, add on 3, still gets me to 7. Same sum, different model, right? All right. It's also, addition is associative. You've seen these properties before. What associative means is that I can organize the addition in any order I want, and it's still going to work out. If I added B plus C first, because they're in the parentheses, and then added A, fine. If I added A plus B first and then added C, fine. It's like if I had 2 plus 3 plus 4, right? Or I did 2 plus 3 plus 4. Well, this would be 7 plus 2 is 9. This is 5 plus 4 is 9. Going to work out in either direction. The identity property is that there is a unique number 0, which is called the additive identity. That for any whole number A plus that number, A plus 0, is the same as A, is the same as 0 plus A. It's the thing you add to any number to keep it just where it is. This is what the identity property looks like as a set model. B is an empty set, okay? N of B is 0. So if there's nothing in it, I'm adding nothing to this other set, so I get the same number back. Subtraction is the inverse operation to addition, okay? Kids know that one undoes the other. When you add, it's the opposite of subtracting. When you subtract, it's the opposite of addition. So for any whole numbers A and B, if A is greater than or equal to B, then A minus B is the number C such that B plus C is A. Okay, now think about that. So A minus B is C, right? And then B plus C is the same as A. And that makes sense if you put numbers into place, okay? So think about that with whole numbers in it if you need to. It's okay to replace things to make sense of them. Remember, in this case, we're talking about whole numbers. We're still not talking about fractions or decimals or any kind of negative numbers. This is just for whole numbers, this definition. So there are 4 models for whole number subtraction. They very much compare to what we were just doing. So we have a set of objects in a set. We can take some away. It's a very common way to start talking about subtraction with kids. You have 5 brownies, you give 2 to a friend, how many are left? Or I had 6 toys, my sister took 2 of them, how many are left? Okay, you take things out of the set. The second model is the missing addend number or model. So it's a connection between addition and subtraction. This is very much the beginning of algebra, where a set is something missing and they have to fill it into place. So if I say set A had 6 things in it, but now I only have 4 things, what's left? How many more do I need to have my 6? Okay, so if we think about this as an equation, it would look like this. 4 plus something is 6. Little kids would see it more like this. They're more likely to just have like an empty box here, right? 4 plus something is 6. This is a missing addend problem, but this is a subtraction problem, isn't it? Because really what goes in this box is 6 minus 4. So we know it's going to be 2 because I need 2 other things to complete my set. But this is where kids start to get the idea of inverse operations. We can also do comparisons. We don't do this in addition the same way. It's just it's a subtraction model. So when we take objects and we match them one-to-one correspondence, we look at what's left over. So it's something like, in many cases, this is a who has more kind of comparison. It's a subtraction. So Sue has 4 blocks, Steve has 6. How many more does he have? Well, they both have those, they both have those, they both have those, they both have those. We've matched these one-to-one. And what's left is that Steve has 2 extra. So really, I had 6, I took away the 4 that I matched, and I ended up with 2. Okay, and it is important that we take the physical model or even the drawing and translate it into numbers and into symbols so that kids start to go between these two and can be fluid and flexible in writing equations. The number line models is the same with subtraction as with addition. Okay, it's just that this one is still not right. That line should be there. This line is bad. Use the green one. Okay, so I start my first vector with my first number. I go from 0 all the way to 10. But from 10, when I subtract away, I go backwards. Okay, so from 10, I go back and take away 4. The result, the difference, is still at the terminal end of my second vector. I still get to 6 here, okay? So I think about it as 10 minus 4, okay? And that gets me 6. A lot of times what you'll see is kids will draw an extra vector here and show where they meet. So this is 10, this is 4, and this is 6, okay? All right, there is another game here. This is 3, 2, 1, okay? It is read the directions and try it, okay? It will be a part of your written assignment. Remember though, when you play this game, the one thing I will say is you are a grown-up. You will get it very quickly, but imagine that you are a second or third or a fourth grader playing it and think about it from that perspective. Encourage the person you play with to do the same because otherwise you know how this is gonna work, okay? There does need to be a little bit of strategy because your goal from 21 is to take turns subtracting 3 or 2 or 1 so that the person that subtracts last and gets to 0 is the winner, okay? All right, so then the question that we're ending with is subtraction of whole numbers closed based on what we know? So if we think about a set, right? Let's think about, ooh, it's a terrible bracket, set A. Let's just put a couple things in. Maybe we have 1, 2, 3, 4, 5. Okay. In addition, we learned that the idea of closure is that I can combine any two numbers in that set using that operation and have the result be in the set. So I could do 5 minus 1 and get 4. I could do 4 minus 1 and get 3. I could do 2 minus 1 and get 1. Okay, that's okay, but here's the problem. I could also do 1 minus 2, or 1 minus 5, or 3 minus 4. And those are negative answers. And those are definitely not in my set. And they're not even in whole numbers. So subtraction is not closed, okay? Just as an operation. It just doesn't work that way because we can't, subtraction is not commutative. We can't go in both directions when we subtract and get the same answer. 4 minus 5 is not the same answer as 5 minus 4. All right, so there will be a second video for 3-3. Please make sure you watch both videos and look at the notes before you move on to doing assignments. All right, I'll see you guys in the next video.